Flexible beams are widely used in compliant mechanism-based precision systems, so it is important to understand how these beams should ideally be assembled. We generally use closed location pins to constrain the degrees of freedom of the beam. As shown over here, the pinholes on the beam have been given location level tolerance so that the pins can slide through these holes precisely. The same tolerance is given to the fixed beam holder as well. In contrast, the screw holes on the beam have a larger clearance so that slight misalignments in threading holes do not cause any extra constraints in the beam. The pinholes in the clamping plate are also sufficiently large due to this reason. It is important to remember that the design you conceptualize has enough space for inserting or tightening of the screws. Care should be taken that the assembly and disassembly of the components is easy. Here is a very important point. The tolerance that you select for location pins has a major bearing on the quality of flexure mechanism. Interference fits and large clearance fits should be avoided at all costs. Generally, we use H7-H7 combination for the pinholes. Look at the general design process video to understand the process of determining the numerical tolerances from hole and shaft combinations. Sometimes it is required to design holes into a part at different orientations. In such cases, it is a good idea to switch to the hidden line visible mode in SolidWorks and check if these holes are interfering with one another. Also, if you want to check whether the overall assembly of the components is proper, you can use the clearance verification and interference detection features in SolidWorks. Another important point to remember is to allow for sufficient material near the edges of the holes. As it can be seen in this figure, the stress flow lines get crowded near the edges of the holes, and to avoid such failure, sufficient material should be provided there. As a thumb rule, at least 2 mm offset should be provided from the edges in case of holes. Encoder mounts need to be designed so as to resist deformation in multiple directions. Location features are a good way to do this. Here it can be seen that the arrangement of the encoder prevents the motion of the encoder mount in X, Y, and Z directions. For a successful threaded joint, sufficient number of threads need to be engaged. As a thumb rule, at least 4 to 5 threads are needed for proper clamping. This is an optional step. However, providing a slot for encoder strip location does ease the process of aligning the encoder considerably. Therefore, wherever possible, this should be included. This is a very important point. Very often we need to change the thicknesses of the beams in the setup. But if the clamps are on the same side, we will not need to change any part design to accommodate for this change. So every time it is important to ensure that the clamps are on the same side of the beam. Observe the gap between the clamping plate and the surface of the bottom plate. This gap prevents the setup from getting over-constrained. The length of the beam is also reduced slightly to create a gap at the ends and to allow for a smooth assembly. While designing the setup, and especially when selecting the position of the posts or clamps which are to be fixed with the breadboard, keep the pitch of the breadboard in mind. The Hallmark breadboards have a pitch of 25 mm, and so if you plan to fix the setup on the breadboard, know that the distance between the posts should be a multiple of this pitch. A detailed consideration of this topic is included in another video. Please have a look at it. Always provide chamfer or fillet on the sharp corners of the part that functions as an effective shaft. Milling operations generally leave round corners on the effective hole, which is equal to the milling tool radius. This can interfere with the sharp corners of the effective shaft and hence we need the chamfer or fillet on these edges. A detailed consideration of this topic is included in another video. Please have a look at it. The moral over here is to avoid sharp corners as much as possible so that we can avoid stress concentration. Shown here is the general format for a manufacturing drawing. It is always a good habit to include a general tolerance table as it makes it easy for the manufacturer to quickly evaluate the cost of manufacturing. Geometric dimensions and tolerances should also be included in the drawing along with indications for material, number of units, the maximum corner radius, and the units of the dimensions. A detailed consideration of this topic is included in another video. Please have a look at it. The most important thing to understand in this slide is that the machining cost of any component varies exponentially with tighter tolerances. So over-precise tolerances should be avoided at all costs. Making tolerance table in the manufacturing drawing as discussed previously can help reduce cost as well. If we consider the top and the bottom pictures, you will notice that the manufacturer has to start with a larger envelope dimension in the top figure. This leads to heavier components and more material wastage. Pushing the pinholes and screw holes up in this case reduced the wastage by 50% straight away.